All right, so let's get started. Thanks so much for coming. So, well, today is my greatest pleasure to welcome Dr. Nikolaus Troje from I'll try. From York University to give us talk at our department colloquium. Professor Troje received his PhD in biology from the Albert Ludwig University in Freiburg, Germany, in 1994. And later, he conducted research at the Max Planck Institute of Biological Cybernetics in Tübingen. From 1997 to 1999, he spent 2 years as a visiting professor at Queen's University in Kingston. Then he came back to Germany in Bochum in 1999, and he founded and directed the Biomotion Lab. In this lab, he established the very first motion capture system ever installed in psychology research lab, while other places using the same technology were making films, such as Titanic. In 2003, he returned to Queen's University as a full professor in psychology and computer science, and as a Canada Research Chair in Vision and Behavior Sciences. In 2018, Dr. Troje moved to Queen's University, from Queen's University to York University, and joined the Center of the Vision Research and as a Canadian Research Chair in Reality Research. Well, he has received a significant amount of awards throughout his research career, including the Volkswagen Young Research Award, ANSER Stacy Award, and the prestigious Humboldt Research Prize, which is awarding him his research as a lifetime achievement, which is very, very prestigious. From 2003 to 2013, he was one of the senior research fellows in CIFA's Neurocomputation and Adaptive Perception program. And this program helped develop deep learning that we so know about, and under the directorship of Jeff Hinton. Well, Dr. Troje's work and research has focused on many topics, including face perception, biological motion, body perception, and more recently, focusing on the people perception in the context of communication and in space and time, while making extensive use of virtual and augmented reality technology and make his research being able to manipulate perception and action loop, and that which is something he's going to introduce today. So please join us to welcome Dr. Troje.
Yeah, thanks, Gabriel. Is my mic on? If I speak like that, it's fine. Yeah. Thanks so much, Gabriel, for the introduction, and thanks for inviting me to McMaster. Again, I've been here before, but it's been a long time. I've been here before actually a couple of times. I think the first time in 1999, when I bet it was Elisa Secula who invited me, and I probably talked about faces and face models that like we developed at that point. And then I spoke in this seminar, or like similar seminar series, I guess, again in 2004, and at that time I probably talked about biological motion, which is maybe the, like I often switch topic, but that's probably the one that I spent most time on in my career, different aspects of biological motion. And then I came back in, well, I'm not sure, I came back, maybe it was 2011 now, is that correct? Yeah. For a meeting where we were, like a couple of colleagues, initiated by Mel, here by Mel Rutherford and Valerie Kuhlmeier from Queen's University, where we put together a little book, not a little book, a quite substantial book on social perception, and I had a chapter in here. And then I never came back, so I haven't been here since 2011. And I just figured that I don't find my way around campus anymore, and everything looks new and exciting. And I'm very glad that I'm here now. A couple of things have changed since I visited McMaster the last time, I moved from Queen's University to York University, as Gabe said already. That was in 2018. And then COVID hit and messed everything up, like lots of the plans that I had. But it also, as I will be commenting on, it also triggered some new research directions. One thing I did during those, like the previous slide I put up to say that I've been faithful to myself all these years working on people perception. So I worked on faces and I worked on biological motion, and more recently I worked on 3D body models and the information they contain. But I always worked in those contexts. I always worked on what I today call like open loop systems. Open loop meaning there's a stimulus on the screen, and there's participants and observers who look at that stimulus and provide some kind of responses, but those responses do not depend, or the stimulus doesn't respond to the responses. So it's an open loop system. And lately I became interested in communication, and particularly in dyadic communication, where one person is the stimulus for person B is the stimulus for person A, and person A is the stimulus for person B, and so we are getting into closed loop person perception, if you want. So that is, yeah, and then like around the same time when I was switching from, it was probably before I switched from Queen's to York University, for related reasons I became interested in the differences between visual perception of pictures and projections, so pictures in a wider sense, including moving pictures, but projections on the one hand as compared to vision in the real world. And of course it's an interesting theoretical question, but it's got very important, very important scope into vision research itself, because we do so much work in vision research with pictures and projected surfaces, assuming that what we learn in such experiments generalizes in the real 3D world. And we want to talk a little bit about that today. Which brings me to my to the plan of, or to the outline of my talk today. So I want to start talking about differences between visual perception of pictures on the one hand and their reference in the real world on the other hand. And then I want to talk a little bit about a tool that we developed to do such comparisons in virtual reality, a tool that I call the Alberti frame, for certain reasons, that allows us to manipulate two major cues, like depth cues, which are processed differently between pictures and real worlds, namely binocular disparity, stereopsis, and motion parallax. So the Alberti frame being used to manipulate them separately, which is generally coupled in the real world. We then talk about depth from motion parallax that restores something that I will be calling directionality, and we get to that. And the directionality is actually is the key concept for everything that follows, and in my opinion plays a crucial role in what we could call a sense of place. Then we will be talking about, that's the first part of the talk. The second part of the talk, I will be talking about video communication. So we will be talking about Zooming and Skyping and similar telecommunication systems, and particularly the fact that we lose lots of the nonverbal directional cues that you have in face real world communication, particularly eye contact behavior. And then I want to show you a couple of, I point out the problems with video conferencing and demonstrate some, our attempts to solve them. Gabe and a couple of others here at McMaster's are hopefully interested in those topics as well, but I know they're interested in some technology that we developed in order to study them. And at the end, I want to talk a little bit about how we employed Apple's True Depth camera and the associated AR-Kit API to build new video conferencing systems that bring back into the game natural, dynamic eye contact behavior, but can be used for all sorts of other things as well. And like this morning, we talked a lot, and I was impressed how far Gabriel and others have taken that already. Jesse here has put together a very nice tool for that. But let me start talking a little bit about 3D space. So, well, I want to start talking about the differences between perception of pictures as compared to perception in real 3D space, and just want to spend 2 minutes on talking about what real 3D space is. Space is everywhere. We are always part of 3D space. It's so ubiquitous that we forget that it's something very special that deserves to be described. That has been done a long time ago, about 300 years before Christ, actually, by the Greek mathematician Euclid in a very elegant way, which I think no one has further condensed. So in terms of, he described space having like 5 independent degrees of freedom, or not degrees of freedom, but 5 independent descriptors, which if they are all, which are all properties from which pretty much everything else that normal experienced space in scales that matter for human behavior contain. So those 5 axioms have been reworded, and there's many different versions of it, but the essence is always the same. The first one being, for any 2 points in space, there exists one unique line connecting these 2 points. Seems to be straightforward, right? Second, a straight line segment can be extended indefinitely. So if you can connect 2 points, you can continue that line in one direction and to the other direction. A circle can be constructed uniquely, unambiguously, when a point for its center is determined and a distance for its radius. All right angles are equal. So that's a funny one, and we don't have to deal with it today, but I list it here for completeness. And finally, for any given line, L, and a point, P, not on that line, there exists a unique line through P, there exists a unique line through P not intersecting with L. So that's the axiom about parallel lines, right? I'm mostly interested in the first one because that one is going to be violated badly in some spaces which have become very ubiquitous to us lately, say. So pictures particularly violate the assumption of the Euclidean space. The critical thing that makes pictures different from normal Euclidean space is what we often call the Mona Lisa effect, which, by the way, I think is a misnomer, or it's an unfortunate term because it's got nothing to do with Mona Lisa per se, of course. Namely, like if you look at a picture like Mona Lisa here, you probably feel being looked at, right? And you feel being looked at as well. And everyone else in the room feels being looked at too, including myself, no matter whether I'm here or whether I'm here. So she follows me with her eyes, even though I don't see motion when I walk from one space to the other, from one location in this room to another. the space, like if we look through that frame into the space that contains Mona Lisa and all that imagery behind her, in that space we don't have a real location. At least we don't have a location that we can control. So we might be adopting the location of the camera that took that picture, if it was a photograph, or the location of where Leonardo da Vinci was when he painted that woman in the first place. But that location is fixed because the camera is fixed and the location of the painter is fixed. So we don't have a location in that space that behaves like a location in the real world, namely one that we have control over. Yeah, this is actually a picture I took the only time I really saw the real Mona Lisa at the Louvre in Paris many years ago, maybe 10 years ago, or probably more than that. So this is where you can't see her, but this is the original Leonardo da Vinci Mona Lisa, unless they put up a fake, but I think it's really the real one. And no one can see her, but all those cell phones hopefully get a picture, and in all those pictures, no matter whether it's this cell phone or this cell phone, Mona Lisa is looking right into the camera, right? That's the Mona Lisa effect, which of course has got nothing to do with Mona Lisa itself. So you could have called it the Uncle Sam effect. So Uncle Sam is pointing at every one of you right now. Or you could call it the zoom effect. Oops. Well, Uncle Sam is pointing at every one of you. If he was, we don't know what he says. Originally he says, we need you for the American army or something. That was an army recruitment poster. When I was a teenager, this poster was everywhere up in Germany, at least. I don't know whether that was here the case. Was saying, "Have you had your pill today?" And so it's been abused for all sorts of different ways. If Tim Hortons, if Canadian Tire would be abusing this poster to when they, or well, if you are seeing it in Canadian Tire on a screen, because Canadian Tire is thinking about getting rid of like the few staff they still had, replacing them by an avatar on screen, and they say, this is the direction of the plumbing department. This person would turn around 180 degrees and walk in this direction. This person would be walking in this direction, and this person would be walking in this direction, right? That's the Mona Lisa effect. And this one illustrates very nicely that there is no unique line between 2 points in space anymore. So well, Uncle Sam and the person here would disagree about what that line is, and we get back to that. Yeah, this one is the last example here. You could call it not Mona Lisa effect or Uncle Sam effect, but zoom effect. It's the zoom effect. This one is a person trying to talk to you on Zoom, and he looks at your image on screen, but there's this disparity between the camera location up here and the picture on the screen here, so you feel being looked at too low. So the Mona Lisa effect is you can't just go down and capture this person's gaze. If you just go down, he's still looking too low. He's always looking at your chin or at your neck, no matter where you are in the room or how high you are. Right? So that's the Mona Lisa effect, which shows very nicely how pictures or extent, like moving pictures, videos, projected surfaces violate Euclidean, Euclidean space. On this slide here, I'm listing a couple of differences. Well, the first point is not really a difference. The first point here that I'm making is just to remind you that when we talk about pictures, we might mean one or the other, or maybe both, sometimes at the same time. So pictures can be two things, or pictures are two things at the same time. On the one hand, when we talk about the picture, we might talk about the medium. So the picture having a heavy wooden frame and a canvas, and maybe a generally planar shape. but the object is a tangible, graspable object in 3D space, that picture. Or, so then we are talking about the medium, the frame, the canvas. Maybe it's a computer. That's a picture here too, in a way, right? Or we are talking about the depiction, so the scene that is presented in the picture. And often it's clear from the context whether we mean, when we talk about a picture, whether we mean one or the other. In most cases, we don't really think about what we mean by it when we talk about picture, but it's a term that has to be like used with care. So if you say, for instance, this picture is three-dimensional, it's not clear. Do you want to say that, yes, like it's a frame and a canvas and I can grab it and hold it like this or like that, it's three-dimensional? Or do you mean the picture itself has something three-dimensional to it? Maybe it's a screen with and you look at it with shutter glasses, so it's a 3D picture. So we can talk about pictures either in terms of it being the medium or in terms of being a depiction. All the other points are points that you want to consider when you think what the differences are between looking at a picture as compared to looking at objects in 3D space. Field of view subtended by pictures is generally much smaller in terms of visual angle than the real world, which is seems to be everywhere, including behind your head where you don't see anything anymore. Two very important depth cues that distinguish between pictures and their reference are binocular disparity and motion parallax. Binocular disparity, so for pictures, of course, if you look with your two eyes at a picture, binocular disparity is not zero necessarily. It's not turned off. You're looking binocularly, and binocular disparity tells you something about the distance and the orientation of the medium, the frame, the canvas of the picture, but nothing about the depth of the depicted scene, the depiction, right? Same thing for motion parallax. If you move a little bit in front of the picture, which is set up on the wall or on the beach, like here, motion parallax responds to the medium, to the frame, to the canvas, to the tangible object onto which you project or is projected the depiction. It does not respond to that depiction. Spectral radiance, by the way, is a cue that is not often mentioned in that context, but probably important. If you're looking at a picture, you are dealing with at least two different illuminations. Like when the picture was taken, there was light, and there was either a flashlight of a camera or natural light or whatever, or the painter imagined some illumination when the picture was generated. That's one illumination. When you're looking at a picture, once it's taken, you also need light in the room or outside. And that light might be different, and in general it is different, and has got nothing to do with the illumination that you had when you took the picture. And so spectral radiance and these two different illuminations might give you cues as to whether you are looking at a picture or you're looking at 3D space. That's, by the way, one of René Magritte's several incarnations of the human condition. He called, like that was a title, not just of that picture, but a whole series of pictures that played with the same topic. So some landscape, some scenery, and then a frame where it's not clear whether it's an open window frame, if you want, or a canvas with something on it. This is one example of the human condition where he reveals, or he provides a solution. So here you know that it's a canvas and not an open frame because of the different illumination that you get here. So this fire is reflected here, and it would not have gotten reflected if that was an open frame. In other pictures of that series, you wouldn't know, is it an empty frame or is it a picture? I mention here accommodation, so how you how you adjust the shape of your lens to the distance of something. If this one was in the real world here, accommodation could, in principle, tell you something about whether the canvas is at a distance of whatever 1 or 2 meters, or whether you're looking directly at the landscape, at this like the sea behind it, right? Accommodation. Size and projection, I want to mention here that. Like in this case here, in the human condition, in all the paintings by René Magritte, picking up on that topic, it seems that the vantage point from which this picture here was taken is the same point from which the whole scene here was taken, and that is the reason why everything lines up nicely. My point here is that only from that one vantage point, if you look at a picture, there's exactly one point where both the size of whatever you see on that picture and any affine distortions are the same as what you would be getting if you were looking at the real scene. So in principle, any deviation, like if you move away from that vantage point, in principle you get information that tells you that you are looking at a picture apparently and not at the real world. So all these points, not the first one, but all the other ones, are in principle at least cues that could tell your visual system whether you're looking at a picture or you're looking at the real world. I just want to say 2 more points about those very central depth cues, binocular disparity and motion parallax. When I teach, when I have my second year sensation and perception class on depth perception, I'm using drawings like this one here and the next one that I'm bringing up in a second here on the same slide to explain how motion parallax works and how binocular disparity works, and that the two are, in terms of geometry, very, very similar. So here I would be explaining, do I have a pointer actually? No, I think I can take this one. Here I'm explaining to students that, like I start with motion parallax, I said you have only one eye at a time, and you are moving this eye from one location here to a different location here. And while you are fixating on this point, and you are attending either to this point or to this point, to a point that is farther away than fixation or closer to fixation. And now you're observing on your retina retinal motion. So the point that you are fixating doesn't move by definition. That's what fixation means. So so you're fixating this one. You keep it on your fovea, at the center of your fovea. But as you do, the picture of both B and A move on your retina. A moves here counterclockwise in that projection here, and from this location to this location over here, this one here, and B moves in the other direction at a smaller distance. Yeah, and of course the geometry is crystal clear here, and one moves in the other in one direction, the other in the other direction, because one is farther away from fixation, one is closer. The very same drawing you can use to explain how stereopsis works, how binocular disparity works. The only difference is that now both eyes are, nothing is moving here, but you sample your image from the location of the right eye, and then you sample your image from the location of the left eye, but all the computations are perfectly equivalent, of course, and the drawings are equivalent, and nothing about that. So I'm pointing that out here because later we get to talk about the fact that there are critical, very critical differences between stereopsis and motion parallax, and maybe just to point at them here already, just want to say that motion parallax in contrast to binocular disparity is what we call a sensory motor contingency. So, and in fact, motion parallax is a very good example for a sensory motor contingency. So a situation where we are actively doing something, we are sending something down our motor system, and we are observing what's coming in through our sensory systems in response. And we can play with that. We can move a little bit, or we can move much larger, or we can move from here to the other corner of the room. And at the same time, we are getting some changes in our retinal image that become, in the course of our visual development, predictive. And that way we learn something about the geometry of space and how it depends on us being agents, and we learn how we change location in space and occupy place. So we learn the sense of place. That's not the case with stereopsis. So stereopsis, there's not the equivalent to the active motion that we do in binocular for motion parallax. So the interocular distance between the two eyes is fixed, and we can't do much about it. And which is one reason why I always thought that both in animal systems, there's interesting work on barn owls in that respect, who also have very frontally placed eyes, but also in human visual development, that motion parallax probably comes much earlier as it like being a sensory motor contingency, and is then used to calibrate the stereo system. And I get back to that because I want to show you one experiment, few slides down the line. Before I do so, I just want to say that this last point here. So I mentioned like pictures are correct for the viewer. Like if you take it rigidly, they are correct only from one particular viewpoint, the vantage point, the point from which the picture was projected. And if you move away from that point, they undergo distortions which make them which make the retinal image different from what you would experience if you were looking at the real 3D thing. Of course, making this point somehow implies that the purpose of the picture is to create a retinal copy of what you would be seeing if you were looking out into the real world. A good picture is one that is as close as possible to what you are seeing out there in the real world. So a good picture is what René Magritte is presenting here, something that is indistinguishable almost from the real scene, at least from the vantage point. Of course, that claim you don't have to sign. And for a long time, people didn't think about pictures in this way. This one is medieval, like a medieval picture, which probably never attempted to represent the view through a window. So it's very symbolic, and people would understand the symbolism of that picture, and it contains lots of important information, probably, but it was never meant, probably, as a depiction of what you would be seeing if this was not a picture frame but a window frame, right? That was different earlier in time. So if you look at, there's not many pictures that we still know of printed during European classics like old Roman and Greek times, but there are some. So one example are those wall paintings in Pompeii. So the site were within one afternoon that volcano Vesuvius was dumping, I think, 9 feet of ashes, and lots of people died in that city of Pompeii, and everything got perfectly preserved until it was discovered in the, I think, late 19th century. And those pictures look much more like the view through a window. So they knew about linear perspective, and they knew lots of things which had gotten completely forgotten during the Middle Ages and were only rediscovered during the Renaissance. So you have two examples of very early works where that go back to like early rediscoveries of linear perspective, who were like first made popular by Filippo Brunelleschi, who never wrote much about it, but he was an architect in Florence, Italy, who left lots of interesting architectural work, but really popularized was the reinvention of linear perspective by, this is just another one to show you more examples. Here, that's perfect. So this is 50 years later from these very early ones, and you already get perfect perspective there. But it was popularized by a guy named Leon Battista Alberti, and I'm mainly mentioning it. So he wrote a little book which is still in press, if you want, not in Latin anymore, but in English translation. Leon Battista Alberti was also an architect and a mathematician, and very good in many disciplines. This one is the Basilica Santa Maria Novella in Florence, just behind the train station. So if you ever get through Florence, it's where he designed the facade, not the whole thing. So depending on from which discipline you come, you know about Alberti, different things. I always imagine, like Alberti is the one who, in this book here, describes to fellow painters how to use linear perspective and how to create pictures that look like a view through a window. And many people, including myself, imagine him. This is my rendering of Leon Battista Alberti sitting in front of the Basilica, which in real life he never saw. So it was built or was finished after he passed away already. But I imagine him here in sitting in modern Google Florence here, looking at his Basilica and reenacting how he learned about linear perspective. So he would set up like a frame through which he looks at the Basilica. It's an empty frame, but he's got a frame there, and then he put another frame that has a canvas here, and he now wants to copy what he sees through that frame onto the canvas, okay? And he might, like as an aid, he might have used some kind of grid, maybe that was like horsetail hairs or something long. So he makes a little grid, and then he looks from one perspective, from this location, through that frame, grid point by grid point, and copies what he sees onto this frame, onto that canvas. And that way he learns that things that are farther away project smaller, and that there's converging lines and everything that we know today about linear perspective. And if you look into this little booklet, De Pintura, on painting, you find not this kind of drawing, but it's very clear that he used some setups like those ones here. I'm showing you this one here because I built my own Alberti frame. We built one in our lab. And we wanted to use it to compare vision through a window into 3D space and vision onto a canvas that generates the same optic array as what you would be getting through an empty frame. So our Alberti frame was set up in virtual reality. This is now not Alberti anymore, that's one of my students. And he's got a head-mount display on, which I didn't draw here. And he looks at some scenery in virtual space. And Now I'm setting up a frame. So that frame you can place anywhere in virtual reality. You just put it up, and then you click one of the buttons of the HMD controller, and that takes a picture, meaning that whatever you see from through that frame from that location gets frozen onto a screen, on a canvas, which is now appearing within that frame. Okay. And so you can play with it. It's just a camera in a way, but it's an off-axis camera. So you can place the frame in this orientation and do the same, and then you get an anamorphic projection, right? Because like everything is badly stretched. If I project Gabe under this, and then I look at the picture that I just took, you will be badly stretched horizontally. So anyway, so it's. In VR, we can do a lot of things that we cannot do in the real world. In this case here, the canvas is not reflecting light, but it only emits light. So we are dealing with that issue that I talked about earlier, that pictures generally in the real world always deal with two different illuminations, not this one here. So we can do that, and we start experimenting with that now. But in this case, we get rid of that cue by making sure that the canvas is now emitting light. There's no reflection. It doesn't depend on the illumination in the room. The scene can change dynamically, so if the tree moves or there's wind and the leaves, you would see that. I still call it a picture. Well, now we can, also in VR, no problem, we can replace the single projection that we have here with two projections, one for the left eye, one for the right eye. So we can add binocular disparity here. So now we are looking at a 3D image. And then finally, we can track the observer's head and update the projection in real time. So now we generated a little virtual reality. So both motion parallax and stereoscopic views are now identical to what we started with. So now if we turn on stereoscopic projection and we turn on head tracking and update the image accordingly, we are simulating what we had before. We are simulating motion parallax, and the frame becomes indistinguishable from the early state, from the empty frame that we started with. So now our Alberti frame can be put into four different states. So either it behaves like a window, so binocular disparity and motion parallax is turned on if you want, or I shouldn't say it's turned on because it was never turned off. Binocular disparity and motion parallax behave or respond to the 3D to the contents that was depicted on the screen before, not to the medium, the frame and the canvas. So it behaves like a window. We can also generate conditions which are hard to generate in the real. Well, this one is a screen condition, so we turn both off. So we have a flat screen, both in terms of stereopsis and in terms of motion parallax. Or we have these conflicting situations. So so the frame can behave like a window in terms of binocular disparity, but it behaves like a screen in terms of motion parallax, or vice versa. It behaves like a window in terms of motion parallax, but like a screen in terms of binocular disparity. Yeah. Yeah, and so this one, like if this one was the original window, just the empty frame, and this one is the reconstruction of the original window from the canvas. We added stereopsis and we added motion parallax, and we can turn both off, just one of them off, to generate the other conditions. Using that Alberti frame, and this is one of a few experiments that I want to show you. using that Alberti frame, we ran experiments in virtual reality where we wanted to look at the different behavior of motion parallax and binocular disparity for perceived direction of a person. So in this experiment, you're in a room like this one you see on the upper left camera, and in front of you, you've got a big projection screen. Or I should say you've got a big frame to begin with, because inside the frame you could have like just a normal projection screen, so you would see whatever is projected there, or you could take the canvas out and then you would look through that frame as if it was an empty frame, a window if you want, or you can set up you could implement the other two conditions where the frame behaves like a window with respect to stereopsis but not motion parallax, or vice versa. So that's the manipulation on the stimulus side. And now you are standing here. This is the frame. So we are looking down here. We are looking from above onto the scene. So this is the frame here. We are standing here, and you are now asked. Well, you see the person either standing in the plane of the frame, or behind it, or before it, and you are now asked to orient this pointing person such that he points at one of these targets here, which are also in this room in front of you. So it's a so-called exocentric pointing task. So the participant can rotate that person, and is supposed, like being in this location, for instance, to make him point at this marker here, say. And we use those data to, as a means to ask our participant where exactly, like at which distance they perceive the pointer here. And what we get is, like in experiment 1, participant is always standing here, and the independent variable is where, like at which distance we project the like that pointer here. And here we get data for the 4 different Alberti frame conditions. So it could be a picture, or it can be a window, or it could be one of these intermediate conditions. So I sometimes call this stereo only, but it's not a good term, because of course you're binocular, you've got both eyes open, but you're looking at a flat screen now with your 2 eyes. So stereo tells you it's a flat screen, whereas motion parallax in this condition would tell you that you're looking through a window and the person behaves like that. Whereas this one in the parallax only condition, again, of course, like parallax is functioning as if you are looking through a window, but stereo is still functioning and telling you that it's a flat screen. Right. And what you see here is plotted over what we call the cubed distance, 1 meter or 0 or -1 or 2, -2, over the cubed distance, the perceived distance as as inferred from the angle at which the pointer, we call him, is pointing. And you find that in those 2 conditions where stereopsis is working, is behaving like it's responding to the 3D scene here rather than the 2D projection. Participants are relatively accurate. Only if it's too far away, like this person is maybe at, I forget how far, maybe 3 meters away from the screen, and so this point would be 5 meters away from the participants. So then it starts flattening out. But in principle, you get good reconstruction of the, as long as stereopsis is functioning normally. If stereopsis is not functioning normally, if you can only rely on motion parallax, you get almost a flat behavior. So in all those cases, the pointer seems to be like half a meter behind the projection. He's always behind the projection plane, who was a postdoc in my lab, and now he's doing another postdoc at U of T, and continuing on like with this kind of work, at least to some degree. This was his first experiment. This is the second one here, where the participant now changes location. And not very surprisingly, of course, if motion parallax now is intact, behaving like motion parallax behaves if you look through a window, then let's see what we asked here. Yeah, so what we are plotting here is the angular deviation from where you would orient the pointer if it was a real person in the real world, right? So if we place him at 22.5 degrees, we would expect that participants also respond 22.5 degrees in the real world. And so if motion parallax is responding as if it was a window, we get that behavior. This curve here, like both curves, are a little flatter than one, but in principle they depend strongly on the viewing angle. Whereas if only stereopsis is intact and motion parallax does not provide a cue, then the orientation of the walker does not change. So that's like, in a way, that's a sophisticated replication of the Mona Lisa effect with a couple of small but interesting deviations from it. I'm not sure whether I get to talk about this one, like the angle between the flat curve here that we get through the window, but like a slightly deviating function if we look at parallax only. I might get to that later, but I might run out of time. Anyway, so what we are observing is just the same plots put together in the same, like on the same slide. Like what I conclude from those ones here, or what we want to conclude here, is that binocular disparity determines distance, whereas motion parallax determines direction. So the orientation of the walker, of the pointer here. So even though the geometry, as I said earlier, of stereopsis and motion parallax is in some way identical or very similar, the functionality is a very different one. And fulfills very different purposes. So binocular disparity for distance, motion parallax for direction. Yeah, that brings me back to this one here. I think I don't have to talk about this anymore. I think I said everything here that I said earlier. So the geometry is exactly the same, but functionally, this one here is a sensory motor contingency. I'm in control. The users or I'm in control of where I am, and I can actively move and see what comes back in response. Stereopsis is not a sensory motor contingency in that sense. Motion parallax gives you control over space. It gives you a place, and it communicates what I call the sense of place. Now, what's his name? Barcelona, virtual reality. Who knows who I mean? I'm just missing a name. Anyway, like a lab that worked a lot on vision and virtual reality talks about the place illusion. That you get or you do not get in virtual reality without really appreciating that, of course, there's a sense of place. I know where I'm right now, unambiguously. In the real world, and I know it in virtual reality as well, but if you're in front of a picture, you don't, because you don't have control like about where you are in space. You don't, that's why you don't know your place. Anyway, so this was work. This was work that we did before COVID, and then COVID hit. And we were not allowed to put head-mount displays on people's faces anymore, and for a while we were not allowed to bring people into our lab at all anymore. Many of you experienced that as well. And we had to shift our research agenda a little bit. And at that point I had become interested in one of these four, well, or five Alberti frame conditions, namely, or Alberti frame settings, namely this one. So the one where the Alberti frame behaves like a window in terms of motion parallax, but it's a flat screen in terms of stereopsis, right? And so we sometimes call it motion parallax only, even though you get motion parallax, but motion parallax tells you it's a flat. Motion parallax tells you that it's like responds to the depth of the scene, whereas stereopsis responds to the flatness of the screen. So that condition so this one is when you experience depth only through motion parallax. We start calling it MP depth, depth from motion parallax. So, and we set it up outside of virtual reality, because that condition you can set up outside of virtual reality because you don't need headsets anymore. You don't even need shutter glasses or anything, because you don't deal with stereopsis. So you're looking at a screen, and the screen is flat with respect to stereopsis. What you have to do is you have to track the observer's location in front of the screen, and you have to render the scene on the screen accordingly, such that any point in the change of the observers creates immediately, with no lag whatsoever, a new view of your object. So in the lab we used optical motion capture that I had used for many years and have lots of experience with in real time. Outside of the lab we started to use Apple's RGBD camera, what Apple calls the true depth camera, with the very convenient API that comes with it, which is called AR Kit. It's a system that, those cameras so far only exist on iPads and iPhones, and there was one series of computers that, like of desktop computers, where they also put an RGBD camera into the screen, but never allowed developers to really access it, unfortunately. But anyway, so we work with iPads and with iPhones, first just to track the viewpoint in front of the screen and then update the scenery. So here you see on a Apple laptop. No, this is an iPad actually. It's an iPad here, and here it's a little video which I will be playing in a second. And what I'm tracking, what I tracked when I made this video is not the observer, but the camera itself, the video camera that I used to generate that video. And what you see here is, let's see, I'm moving the camera around, and hooked up to the camera, oops, oh, sorry, I didn't start at the beginning. I think I should start here, yeah. Okay, so here you see that little iPad computer, and I'm just moving the camera around. And particularly for the camera, which is monocular anyway, it looks like you're looking through a window. And here my technician is actually able to interact with the object behind the screen. So it's a window in terms of motion parallax, and here you don't even realize that stereopsis does not work, because you are used to the fact that anything that happens here on the screen doesn't have stereopsis. We used that, like one experiment that I just want to show you here is one that we that we ran with infants, with a colleague that you also know, Gabriel, Gudrun Schwarzer. Actually, this is an older work by Gudrun Schwarzer and Jody Cullum and one of their graduate students, where they showed that children, or they replicate something that was known earlier actually, that children show a preference for real objects over pictures. So they would show infants, in this case 7 to 9 month old infants, two renderings, if you want, of the same toys. So one is really the real toy, a real 3D toy glued onto that black cardboard. It's on the left-hand side, I believe. And then on the right-hand side, you get a picture, or they get a picture that looks almost identical to the real thing. The question is, can they discriminate? And the answer is yes. They look preferably to the real object and not so much to the picture. Our question for our experiment, for this one here, was what is it that attracts children that age, at an age where, on the other hand, we know that they are not responding yet to the affordances of objects. They still grasp at images. On the one hand, they don't understand at that age that something that's depicted on images cannot be manipulated or grasped. But on the sensory level, they seem to be able to discriminate between the two already. So here we ask, is it enough if we just simulate depth in terms of motion parallax? If we assume that motion parallax comes early and then helps the developing visual system to calibrate stereopsis, and motion parallax is advantageous to, or is used to calibrate it because it's a sensory motor contingency, we would expect that much earlier. And so here we showed them, we had 3 groups of children. I hope I have that on the, do I have that on the next slide? No. We had three kinds of displays. So we had the real objects, maybe not even sure which is which. So this one is the real object here in a wooden box, so behind that plane. And then we had the very same wooden box, but now we slide an iPad screen into it. And on the iPad screen, we either show just the image of this one, which we generate computer graphically, so it's exactly the same one, or we show the image with added motion parallax. So we generate our NP depth condition. So we hook the rendering up to the location of the baby, which is always something, and show it with motion parallax. So we simulate depth. That's the 3 conditions here. And then we had 3 groups of children, and presented each group with a choice between 2 of them. So the first group would get 1 versus 2, and the second group 2 versus 3, and the last group 1 versus 3, right? And those ones are the results. Those 7 to 8 month old children now, 60 altogether, so these 3 different groups. So this one here is is replicating the earlier real object effect. That's how they called it. So real objects are more attractive than picture. So that's the iPad without motion parallax. That means it's just a picture. Here we are looking at the iPad with motion parallax as compared to without motion parallax, and they prefer significantly, not super large effect sizes, but significantly and comparable to other infant studies, a preference for the rendering with motion parallax. So for the where we simulate, if we compare that one, so the iPad rendering with motion parallax to the real object, they are the same, pretty much, right? So we confirm that they respond to depth from motion parallax early on, which now gets me, boy, I'm just seeing, I talked already over an hour, right? Is that okay? Yeah. Yeah, I try to, but I need to get to this one here. So we get back to directionality. So I used the term a couple of times, and I said it reflects on whether space is conform with Euclidean geometry. So in the real world, the line of sight between two people, if I talk to you, no matter whether I'm looking at you or not, but the line of sight between the two, so the connection between our location serves as a reliable reference for the two of us to scale in terms of distance and orient at least the horizontal part of the 3D coordinate system within that constitutes the space we are into. If you have another reference like gravity, for instance, it spans your 3D space. So we have then a shared coordinate system within which we agree over orientation. So I'm, in this case, maybe this is me, I'm oriented an angle alpha in one direction away from that line, and so you are 15 degrees to the right of me. From your perspective, I'm 15 degree orient to the left, and we agree on that. We can agree on that because we are dealing with functional Euclidean space, because there's only one line, an unambiguous line that connects the two of us. This is a different angle. Again, we agree. That case is violated. Now we go into Zoom. So this is me, or this is your partner on Zoom looking too low because the camera is too high. You might be able to correct for that one computer graphically or otherwise. What you want is something like this one, but you don't want that all the time. So here I'm now corrected for that disparity between the camera here and the rendering in the center of the screen. But the problem here is still the Mona Lisa effect, right? So now the person is looking at everyone all the time. You can't escape that person's view again anymore. So let's see. So you've got eye contact, but you've got it constantly, and it's not real eye contact probably. Eye contact is super, super important, and I should quickly go through that slide here, probably just saying that there's tons of literature how important it is. One particular paper that's worthwhile looking into it if you're interested in this is Senior and Johnson, 2008, who show that even that the eye contact event itself triggers immediately responses of the autonomic nervous system that you can measure in terms of skin conductance or pupil diameter or heart rate variability, for instance. So there's all sorts of measures that show that with each eye contact event, your body responds, and you can't help that. It's a response. If that happens during Zoom, it happens at moments where the other person's not even looking at you, probably. They are looking to the camera, they don't see you. So it's worse, like if you remember the times with good old phones that had no video. Of course you had no eye contact, but you didn't have any spurious information either. Zoom in a way is, at least in terms of eye contact behavior, is worse than not having visual at all, because you constantly get these eye contact experiences which are no eye contacts, really, right? So this is the situation here, where Euclid's first axiom is badly violated. So this person A in front of their screen, the webcam happens to be here. This person happens to look into the webcam, which means that this person feels being looked at on the one hand. On the other hand, like for another example, this person here is oriented a little bit to the like counterclockwise from the center of the screen here, but the camera is here on the clockwise side, which means that this person perceives this person oriented into the other direction. So nothing is veridical anymore. There is no unique line between those two people that can serve as the reference that is so crucial for interpreting directional behavior in real space. Right? Yeah. Now, what I just mentioned, like if you just compare this situation where the person is looking too low to this situation where I just moved the head up, or maybe I managed to move the camera right behind the screen, that one I often call the teleprompter approach to the zoom problem. But it solves only parts of it, or maybe it makes it even worse, because you still don't get the dynamics of eye contact behavior. If I'm talking to someone and I'm moving, then you are following me, hopefully. If you don't, then because you don't want to listen to me anymore, and I will be realizing that. So eye contact, just as one example for the information contained in eye contact behavior, there's tons of other information that gets missed and misinterpreted in the zoom condition. So in the teleprompter condition would be the one where you move the camera behind the screen, behind the center of the screen. And then now you can have eye contact behavior, but it doesn't mean anything anymore. I'm just moving those, I just moved one of them such that it faces the other one, because to show what we really want to have. We don't want the camera here, and we don't want this camera here. We want this camera exactly where this person is right now. And if this person is moving, the camera should be moving. And then we get the projection that we want. And the same thing on this side. This camera should be moving with that person here, no matter where they are. Yeah, I go quickly through that. So here I'm taking the screen and I'm opening it up as a window to explain what we want. So if this camera would now be projected, so this camera is moving with the person's head, and we are projecting whatever this camera sees onto that screen here. Then I'm simulating a window where both people have can move dynamically. Let me jump over this one here. So we did that, and we did it a couple of times. The last